right, so I'm gonna do problems A through C. I did pretty well. I was able to get A through C. Ironically, I didn't get time to do D, even though D was easier. I think that was because I was just like solving the wrong problem for problem C for like a good hour and 30 minutes until I looked at a condition and I was like, oh my god, I'm stupid. But I was able to get it without a penalty, not bad. And I kind of got edged here. I almost got cyan back, but I've been low-key gaining now. It's like the first time I've gained for like 4 contests in a row. So I've been getting out of this slump that I was in. So yeah, and that's without like training that much. So I'll take it. All right, so let's do problem A. So uh, I'm not gonna explain what the problem is. I'm assuming that if you're watching the video, you already like have read the problem. But this is funny because you can actually guess the solution for problem A. Basically, if you notice, most of these answers are just the number of odd numbers in here, and you just have to add one. In most cases, except for like the edge case, there's some edge cases. Um, but pretty much. But let's just talk about the solution. So the idea is that um, every time when you're about to process the ith element, except for the first element, you always have an odd sum. Because in the first element, you have an even sum. You're gonna have zero before you process the first element. Your sum is zero. So when you can only earn a point on the first element if the first element is even. But after that, you observe that because of this condition that you keep dividing the number by two, but when you're processing the ith element, you're always going to have an odd sum. So the only elements that can contribute from now on are just odd elements. So basically, it's just the number of odd elements you have plus one. And we're assuming that if we have an even number, any even number, we can just put that number in the beginning to have that additional point. So this is the code. Um, it's basically just start with one and then add the number of odd numbers to it. And basically, if there are only odd numbers, basically, I didn't code it like this because this is me guessing the solution. But the way I would code it is I would just count the number of odd numbers and then add that to one. But if there is any, or yeah, but if there are no odd numbers, then I need to subtract one from my answer. I mean, if there are no even numbers, I need to subtract one from my answer. But that's pretty much the solution. This answer minus one case is basically just the number of odd numbers, and if there are n odd numbers in my solution, then I know that like except for the first element, every other element is going to contribute because I'm going to have odd plus odd, which is even, and so I'll just set it to n minus one. Um, if that's not the case, then we obviously know that we have at least one even number that we can put in the front. And if we have one even number that we can put in the front, we can do one plus the number of odd numbers, which is basically what this is doing right here. So that's problem A. Problem B is generalized triangle inequality. The way that I actually figured this out was something. It was kind of weird. I kind of BS'd it. I don't even think it's good to explain here, but it's basically you have to know that um, if you want to form some polygon, some closed polygon, I think it's some convex polygon. I honestly, this is honestly you have to know like this thing, but it's basically just like this is true, right? So let's say this has to be true if you want to solve if you want to solve if you even want to have a trapezoid. This has to be true. The sum of the three shortest lengths have to be greater than the longest length. Um, and we know an isosceles trapezoid, so we're gonna have A. We have to have two side lengths that are the same, and so then we're gonna have B and C left. And so then the intuition is that I need 2A plus. I'm gonna assume that, and then assume that C is greater than B. My assumption is this, or like whatever. Then I'm gonna have 2A plus B. The sum of the three shortest lengths have to be greater than C. And that's like this is like called. You can search up generalized triangle inequality. If you have like n side lengths, then it's like a1 plus a2 plus a3 all the way to an. That's greater than or n minus one. That's greater than an. Honestly, this is just something that you would have to like know. Um, like it's just math. It's not really like competitive programming ish. It's more geometry. So like yeah, whatever. But yeah, this would be your case: 2A plus B. The sum of the three shortest lengths have to be greater than C. And you might be saying, well, what happens if A is the longest side length? Well, then you're gonna have A plus B plus C, some of the three shortest lengths. This is obviously true. Like obviously A plus B plus C is greater than A because B and C are going to be positive. So you don't really care about checking that condition. The only condition you care about is checking is the assumption that A is not the longest side length. In that case, you can just check 2A plus B. That has to be greater than C. You can reduce this to just C minus B. So basically, the condition you have to check is that the sum of the two side lengths that are the same have to be greater than the difference of the other two. And the way you do this is maximize A by and we just maximize A. So we find some element that has another element that is the same as its value, and we want the biggest of that, so that's easy to find. And then once you have that, just find any other two elements that are really close together and check if 2 times A is greater than that difference. So the way we do this is we iterate through, we sort it, and then we find, um, we maximize the A, which is basically the same element, AA, and then we just let this run because it's sorted, so find the greatest one. And then I'm going to just say if there are no elements that are the same, get out of here, just get the hell out of here. Um, Otherwise, what we're going to do is we're going to just, for, out of the two elements that I chose, like my AA, I'm going to remove them, and then I'm going to add all the other elements, and then I'm going to iterate over all the differences, and I'm just going to have to find one um, that is less than 2 times same. So 2 times same is greater than that. And the reason why I only have to check consecutive differences is because obviously those are the numbers. Those are like the when you sort them, you keep the numbers like the pairs closest together. You know what I'm saying? Like for some like obviously if it's sorted, then you only have to check consecutive differences for C minus B. You're hoping you find like a small one, and once you do that, um, you can set B to other dot get I and this to that, and then just print same BC. Boom, got him, coach. All right, so that's the solution. And then let's see problem C. So for this problem, um, basically you have to consider DP on a prefix. So we're gonna have a DPI 0, where we consider answer on ith prefix of array, and the ith element is honest. DPI1, where we consider answer on the ith prefix of the array, and ith element is lying. And the reason why, so we consider DP on a prefix, but we know we have to do casework. The reason why we have to do casework is because the way that we transition depends on if I'm honest or lying. So, for example, if the ith person is lying, then it's obvious that the person before me has to be telling me the truth, right? Because of this condition that says no two liars can stand next to each other. So what I'm going to do is I have to do DPI 0, and I'm going to say, well, the other person has to be honest. So it's basically just the amount of ways in which that person was telling the truth, and then I'm good. Now the other case is trickier. So this guy is going to be lying. So let's say this guy's telling the truth. I mean, let's say the ith person is telling the truth. Well, then it's some casework, right? If the other guy behind me is being honest, then I can also, that's also the amount of ways I can do. I can do this. But if the but this is only true. The only way that H can be honest is if the number of guys. So the only way this can be honest, which is I minus 1 and this is 1, is if this is equal to A sub I. And the reason this is true is because if I want to form a case in which the I minus 1th person is being honest, then I need to make sure that the number of guys it says are lying to the left of me is the same as the number of guys that the ith element says is lying to the left of him. So these have to be the same, because the number of liars in this guy is obviously the same for this and this. So that if I want this guy to be honest, that has to be the same. There can't be any contradiction, right? If this guy's telling the truth, then the number, and this guy's telling the truth, then this has to be equal to this. If I need 5 liars here for this guy to be honest, but I need like, I don't know, 4 liars here for this guy to be honest, both of them can't be honest. So I have to check if that's a valid case, right? And I'd also check. This is what I do: is I check that if the number of guys that I say are lying, a sub I, that has to be less than I, because I have 0 to I minus 1. I have exactly I people, right? That's the amount of people that are left to the 0 index of I, right? And obviously, the number of people that I say that are lying, that has to be less than the number of people that are to the left of me. So a sub I has to be less than I. So I'd also check for that condition to check if this guy's honest, if I can even say this guy's honest at all for the for if the ith one's honest. But that's one case. That's like the case where the guy before me is being honest. Now he could also be lying. If this guy's lying, it's fine. This condition saves me a lot. No two liars can stand next to each other. If this guy's lying, sure, then this guy has to be honest because I can't have two L's in a row. And then it's the same idea. I'm basically saying the number of liars, so AI minus 2 to the left of me plus 1 has to equal to AI, and this condition still has to be true. And this is true because for me to propose that this guy's honest and this guy's honest, then they can't have a contradiction in what they demand for the amount of liars to the left of me. The amount of guys that I'm lying here, which is the amount of guys that are lying here, which is AI minus 2, plus this 1 has to equal a sub I, the amount of guys that are lying to the left of me on I. And so then I have this condition here that has to be true in order for me to uh, add that up. So I can do dp, I minus 2. But these guys are conditional. So this is like a conditional. You have to check the condition. So we conditionally add these. And so then we can check the solution. I'll just show it here. Oops. So what I'm going to do is, these are some base cases. So obviously the 0th person can always be lying. So that's one way. The 0th person can be lying as long as it demands 0 people. The 0th person can be telling the truth as long as it demands 0 people that are lying to the left of it. Then it can be telling the truth. So then I can have one possible way. Now in this case, I know this is my simple case. If I say the ith person is lying, then I know that the person behind me has to be telling them the truth because of that condition. So I just say it's the amount of ways that the amount of configurations in the I minus 1th prefix such that the I minus 1th guy is telling the truth. Boom, I'm done. Otherwise, I need to make sure that, I'm going to say, otherwise, I'm going to do the case where the ith person is being honest. And can the ith person even be honest in the first place? Well, the amount of people that it demands that are lying to the left of it have to be within I. If it's greater than I, you can't have the amount of liars to the left of it that it claims to be can't be greater than the number of people that are to the left of it. So I is the amount of people to the left of it. A sub I is how much we claim to be. Obviously, that has to be within I. You can't have any BS. And so the first case is that if the guy if for I, if the person is being if I'm saying if I is honest and the guy behind me is honest, then I can just add it to my answer. Boom. That's one case. Otherwise, I can assume that the guy is lying. That is behind me, I minus 1. The guy is lying. And if the guy's lying, then I know that I minus 2 has to be telling the truth. So then I can say, but if I'm saying the guy is telling the truth, the condition has to be such that the amount of guys that are lying to the left of I minus 2 plus 1, because we know that the I minus 1 is a liar, that has to equal a sub I, which is the amount of guys that the ith element says that are lying to the left of it. And if that is true, then we can add this dpi minus 2 1. Yeah. And this is just the casework. So if you don't have I minus 2, you might have to do some casework. So for example, you might have H, and you might say we're considering the case where this HL case, and we might not have anything here. Well, LH is only valid if I say the amount of people that are lying is 1. So the amount of people that are lying is 1, and if that is true, then that is a possible case. because then I can just have this guy lie and I'm chilling. So that's basically the solution. It's basically just to consider cases where you have HLH or HH, um, or LH for the ith prefix, right? The ith prefix looks, you basically just do casework on how it looks. It can either be LH, right? Or it can either be HLH, or it can either be HH. Do casework on how it works. It's either LH or HL or HH. Do casework on each prefixes, and it's very easy to count. If you just split it up like that, it's going to be very easy to count the cases. And so it's just like casework. Yeah, pretty much. It is a little bit of annoying to think about, but that's ultimately what you have to do. And it's ultimately just this condition that no two liars can be next to each other. So if no two liars can be next to each other, then there's only so many possible ways to arrange the first two characters from this way: LH, HL, HH. All right, so that's those are the solutions. I will upsolve problem D. Not really upsolve, but I'll try it out, see if I can get it, and then I'll make a video on it. So cool.